So I'm Marcin Rzeźnicki. I work for Iterators. We're a Scala consultancy company based in Warsaw. And I must say I'm very happy to be here for the second year in a row. It's such a great conference that I'm really proud to be invited here. And I'm also happy that John Pretty didn't steal my audience. That's a lot of you here. Thank you very much for coming. So some of you might remember that in my previous year presentation here, I was talking about Idris, the programming language, how it relates to Scala. Today, I'll be talking about something more lighter, about a lighter subject, about basically something that happened to me in my work. So please take heed, because this thing might happen to any of you. So what happened to me in my work is basically this. I got ambushed by a madman. And this madman with this facial expression happens to be my boss. And out of the sudden, like a madman, he ambushed me by saying that he didn't like EitherT. Well, to put that in a context, we had been having a conversation about how we want to write our programs, basically, as a functional developers. So, and if you try to write a functional service layer, then obviously you don't want to deal with exceptions. You want something more type safe, more functional. So soon you'll start using either. That's a very natural type for this kind of thing. And then you'll have EitherT all over your code base. And EitherT is fine, but out of a sudden he didn't like it. So my first reaction was denial, basically. What's not to like? If you take a look at the exemplary code written with EitherT, you'll notice that that EitherT is to a clear, concise, compact code. You can draw a virtual line here that divides this code into two parts, and on the left part, you'll have combinators, basically, that EitherT provides, and these combinators will glue your code together. They will guide your flow, and on the right-hand side, you'll have your business logic. In a very linear, top-down fashion that's easily understandable. You can almost read it from top to bottom and know what the code is about. And all these combinators, they give you a lot of expressiveness. They are, sometimes I call them like stuff for integration, because they enable you to integrate your code with various with other pieces of code that you may encounter, with code that throws, with code that never throws. You have validations, error recovery, or functional error recovery, and so on, so on. So that gives you a lot of expressiveness, and that expressiveness leads to pretty concise code. So that was my reaction. Well, what's not to like? Well, when we started discussing things further, it turned out that there were some things that they didn't like, that my boss didn't like, that my colleagues didn't like. Well, first of all, as you observed, a lot of things are happening inside combinators. So because of this, EitherT doesn't really yield itself to a for comprehension style. Because for comprehension is all about flat maps, and if you try to use flat maps with EitherT, you'll end up creating EitherT instances by hand in flat map closures. So that can start to look really ugly soon. Well, I wasn't convinced by that argument, to be honest, because I don't feel that writing for comprehensions everywhere is necessarily good style. But I'm not sure if that's the case in your companies with your colleagues, but my colleagues tend to write for comprehensions a lot. They naturally gravitate towards writing for comprehensions. So whenever for comprehension is possible, the code will get squeezed as to be a for comprehension. And well, with EitherT, EitherT doesn't really play very well with for comprehensions. Well, also you need to annotate types quite a lot, especially error types. Well, you can check the example again. Well, here, for instance, error types. Due to various issues, you'll tend to fight type inferencer over and over to get them to be right types. So, but I wasn't convinced by that argument either, because, well, we are, after all, Scala developers. So, you know, type inferencer in Scala is not perfect, and for various reasons, it will never be perfect. It can never be perfect. So we can as well just get used to the fact that we need to write type annotations here and there and just accept it. But these were the first pain points we discovered. Then, well, allow me to rant a bit. If you see a piece of code in Scala that's very clear, concise, reasonably good looking, then this code most probably doesn't compile. And the example I showed you, it doesn't compile because of variance issues. Well, it's easy to be fixed. Just follow the error message here and add whatever craft is needed somewhere to your types. It will even tell you that it's about variance, but it can be infuriating to, you know, to fight type system in your code base. Also, if you think of how EitherT plays with composition, by composition I mean where you have two independent services and you want to glue them together in one piece of code, then writing this code can become tricky, basically. If you write it naturally, you just call one after the other, it won't compile. You have three factors here at play. There's a type inferencer, there's the way how for comprehensions are the sugar to flat maps, and there is a variance. So all these three factors will bite you. Now, the natural way to write it doesn't compile because types do not match. So you'll be throwing a towel, you'll throw a towel and say, all right, I'll just take the type inferencer out of the equation, just annotate all the types by hand. But then variance of EitherT will bite you because EitherT is invariant in its error argument. So here the error types won't match and it doesn't compile. You'll throw a towel once again, saying, all right, I just remap the exceptions to be whatever type is needed by hand. But now the way how for comprehension is desugared will bite you, so it doesn't compile. And finally, you'll find the right incantation, which is this. So composition with EitherT is, of course, possible, but you know, especially in larger code bases, in longer pieces of code, that can be infuriating as well, to fight all these issues. And allow me to rant once again. Now, I find it a bit ironic that problems caused by object-oriented programming, namely variance and type hierarchies, are solved by a very, very simple functional programming, namely left map with identity. I find it a bit ironic that that's the case. The reason for this is variance. For a lot of problems I showed is variance. So variance is form a lattice. And if you try to write a very generic abstract code, then you have no way but to specify your higher kind types to be invariant. Why? Because if you made them covariant or contravariant, you would be able to work with effects that are respectively covariant or contravariant only. If you want to work with anything, you'll need to make it invariant. And here sometimes, as you saw, it bites us. Out of curiosity, I tried to see how the language we all look up to, namely Haskell, solves these problems. Well, I'm not an accomplished Haskeller myself, so I just checked Matt Parsons' blog to see if there are any issues, how they program this stuff. And it turns out that Haskell doesn't have much better story in this regard with respect to either-based code. So essentially in Haskell you see the same thing. Here you have your composition, your sum type of all your errors that you invoke, and you need to write by hand all this map left here to message the error instance to end up in the right place to match the error type. And this is pure boilerplate, just as in our example. Well, you could argue that that is compiler guided thing. You cannot get it wrong, because if you got that wrong, your code wouldn't compile. But still, if you change the order or add something, then you need to refactor everything, and that's pure boilerplate. So, admittedly, Haskellers, they adapt other techniques to elegantly solve the problem. Things called classy prisms. I won't bore you with details. Just check Matt Parsons' blog. But they have other elegant techniques to solve this. Either doesn't look much better in Haskell. Well, what would be perfect would be to have a type, a sum type, that's independent of the order of its components and open. By open, I mean that it can be unified with type that has the same type constructors or more. So it turns out that there is a language that has something like this. It's OCaml, and in OCaml it's called polymorphic variants. I'm not sure how visible that is. Bad? This one is better. It's more bright, I would say. Anyway, the example is not that important. So you have 3 separate modules. You have each module has its own respective error type. Here are the variants, but the gist of it is here. So function from every module says that it can return an error type or the error type from the module it's in, or bigger type. And then when you combine functions from all these modules, you'll have a perfect type inferred, independent of the order of your composition and having everything, inferred automatically and in place. So that would be the perfect solution for me. That's in OCaml. We don't have that. So okay, let's move on. So if we don't like EitherT for various reasons, then hey, maybe let's recommend to our developers to use MonadError. MonadError is another widespread, almost ubiquitous technique of functional programming that is for dealing with errors. For those of you who don't know what that is, so MonadError is an abstraction over monad. It abstracts over monad that can additionally handle an error of some type. So MonadError of M and E exists whenever monad M can handle errors of type E. For instance, there is an instance of MonadError for a future and throwable, because futures can naturally handle errors of type throwable. Ditto DBIO. Also, there exists MonadError instance for any monad and either, because as we observed, you can put either into anything, into any monad. By the same reasoning, we have MonadError instance for any EitherT. So that's actually a generalization over EitherT. And technically, MonadError extends monads and adds various combinators for dealing with errors that can be hidden in the monad. And if you try to rewrite our example with MonadError, you'll notice that, well, some of you will notice, guys on this side, you'll notice that the code is reasonable looking as well. Well, some things get moved it's more natural to write it as a flat map, because by the virtue of being monad, flat map is really a natural start to write this kind of code. Combinators are moved here, but still it's a quite good-looking, concise piece of code. It eliminated one of our pain points. We can now... is it better now? Oh, thanks. We can now naturally use for comprehensions, well, by the virtue of being monad, right? Also, because error type is explicit here, is explicitly given, then we don't have to annotate error types anymore. So it really helps with our another pain point, which is type inference in flat maps, or basically type inference. So it looks perfect, right? We eliminated all our pain points we had with EitherT. If you tried to recommend that to your developers, unfortunately, they wouldn't be that happy. Well, first of all, this technique is very, very invasive. What that means, if you take a look at the old example here, and the example were written using MonadError, then first you'll notice that all the methods, the signatures of all the methods are changed. So where your methods return something, they start to return something else, like EitherT instead of not EitherT. So if you try to refactor your code base using this technique, it would be hard. It's not really suitable to be incrementally applied to your code base. Either you started with MonadError, or you didn't, and then incremental refactoring the code, with MonadErrors, you would end up in a state of a mess. So your developers won't be happy about it. Also, if you think of MonadError as a type, as an interface, as a type class, then well, it can lead to a bit nonsensical or awkward code. There is a very instructive critique of MonadError by Luka Jakobowicz. I would recommend you to read that. It's titled Rethinking MonadError. But basically the gist of it is that MonadError uses just one type to distinguish things with that can have errors or have errors handled. Basically, you cannot distinguish that. What that leads to is that, for instance, you can chain attempt indefinitely. That would be type correct, but it will lead to a type like f of either nested deep down. So that's nonsensical. Just by looking at type signature of some of its methods, you cannot say what will happen. You cannot say if your error handling function can throw errors, and if so, what happens when it throws. Why is the same time consumed by the function and returned out of it? So what happens? What may happen? You just can't tell. So basically, the contract of MonadError can lead to an awkward, nonsensical code sometimes. Now, composition. When we said that EitherT, well, is composable, but you need to fight it a bit. And then MonadError, I would say, is not composable at all with respect to its error type. It's because MonadError for some bigger type, like here, does not imply existence of MonadError of its component types. So if you go back to the example where we had two services combined, then you can satisfy the services dependencies if they depend on MonadError by using just one big MonadError of with error type set to some common error supertype. You can't. You'll need to carry all the dependencies, all the requirements, all the little MonadErrors everywhere with you, and sometimes that's simply not possible. So I would say that MonadError is not composable at all. Now, there is a war story of mine here. I tried to fix this issue. I even made PR to CATS, but that PR has never been merged and probably never will because there were some issues with it. Now, the idea is here is that you can derive some interesting MonadErrors from some bigger types if you can prove that these types are in a can be substituted one for another. That's sometimes called list of relationship. So I proved it by writing some code. So if you have a big monad error and you need to derive small monad error, and you have list of relationship, think generalized subtyping, then, well, you can write it like this. That would solve all the issues with composability. You'll just need one monad error instance, and it would, well, rule them all. But there are some shady parts here. You cannot write this code without runtime reflection, basically, without class tags. So that was the reason why it hasn't been merged to cats. Also, there were some other issues with this code, namely you couldn't tell what happens. Some errors could be left unhandled, basically. That's what it says. With this automatic deriving, whether it's the right thing to do or not is debatable. So without this PR, I declare monad errors to be, well, not composable at all. Okay. So what's the situation I'm in? There are two very widespread techniques, EitherT and MonadError, of writing functional error handling code. Both of them have some drawbacks. Obviously, there is no silver bullet. But either my boss nor my colleagues, they don't like any of them, and they want me to fix it. Well, and they are very insistent about fixing it for them, whatever that fixing means. How would you fix that? What's to fix here? Well, I told them, just pick a technique, accept its drawbacks, and move on. But we discussed things over and over, and during our discussions, I discovered basically one fact came to light. The fact is that was pretty much important for me and got me thinking was that in our code bases we do not have a type for errors. What does it mean? So if you imagine kind of a login service method, then you would expect to have a login error type that would have as its subtypes things like, I don't know, user not found or account deleted. That's not what they were doing. They didn't have any such a type. What they had was they had single flat login response type, and everything was crammed there. They didn't distinguish between correct responses or wrong responses whatsoever. So now, first of all, I do not like this style. I'm not sure about you, but I simply don't. I would prefer to have error types. But you could argue that there is some beauty to that. First of all, philosophically speaking, user not found is not really an exceptional situation, right? Business as usual. Also, if you recall the previous examples, these deep hierarchies caused us some problems. Now, they sidestep these problems by not having any hierarchies. They just have one single hierarchy for anything, for any possible response. So that got me thinking, well, now it's no wonder that they couldn't use MonadError, right? MonadError is totally unusable in this setting because MonadError needs an error type, and here is none. Also, I understand why it's a bit awkward to use either-based solutions. Well, if you try to use either-based solutions with this style, then you would have to have the same type on the left and on the right of the either. Which means that, first of all, type system is not that helpful. You can make, right user not found or, left logged in, and, with no help from type system. Also, to get a response from your method, a single value which you need to return, you need to do some strange dance, right? Like merge-like methods, pattern match on what you have, and so on, so on. So even though there is some beauty to that, well, I would say that this beauty is in the eye of the beholder. I don't like it at all. But that got me thinking. I started to look at the code base that we had. And that's some code I found. Now, I looked at this code very, very hard, and I discovered some emerging pattern that basically this code is a tree. It describes a computation that's a tree. At the root of such a tree, you bring some data in. You may have some intermediate nodes where you transform stuff or so on, but finally you'll get to your leaves, and on the leaves of this tree you have instances of your response. Let's call it ADT wrapped in some effect. Now I looked at it hard enough, so even the code that didn't look like a tree started to look like a tree. Everything was a tree. And then I said, all right, I will fix it for you. This observation made me say that yes, I'm able to fix it for you. So now, how to create a structure? That structure will be a monad, but that may not be that important. So how to create a structure that will enforce whatever your boss likes in a few easy steps. First step, well, you need to formulate what you want to have, basically requirements. So computations are trees. Leaves are instances of a response type. Let's call it ADT. You might have some intermediate nodes where you don't have yet ADT. Whenever you reach your response, there is no point in continuing the computation further. You just got all the information you need to return a single response. So that's a kind of a short-circuiting. Whenever you reach ADT, you're done. When you flat map over it, you basically make a branch. So you just take the value you have just computed, inspect this value, and decide what to do next. So that's branching. Flat map makes a branch in the structure. You need some combinators, for familiarity, basically, that are more or less EitherT-like. And also, there is no point in having computations that do not return ADT, because ADT is all we need. So for added type safety, we can add validations. We can type level validations that you have to prove that you have reached your ADT. Let's call this rule reach ADT or die. We can enforce that. This is what I want my structure to do, basically. First step. Now, next step, first you need to devise some catchy name. That's the second step. After you devise catchy name, you need to draw some parallels. Let's find something that's very similar to what we want. Observation is here that free monads are what we basically want, because free monads model trees. What free monad is a tree, is a computation tree. Basically, we can say that's the structure of free monad here as an example. If you look at it, it's a tree, just as we want. Now, we could say that our structure, our computations are like free monads that produce either ADT or A. But it's almost not exactly, because actually we don't want to model any tree. We just want to model those that create an ADT finally. So we restrict that. Now, so it's not exactly what we want, but it's sure like a good basis for what we need. Now, let's just copy it. Copy the free monad. So I created a type. I called it sealed. The interpretation here is that the computation sealed under some ADT. So the type signature here says that sealed is a type that operates on effect F, produces value of type A, but is obliged to produce value of type ADT finally. Whoops. Where am I? Ooh. Okay. Okay, so in this structure, we just basically, in this type, we try to cover as much requirements as possible. So instances of this type, we can have three cases. We are either ADT, so we reach the end of our computation, or we didn't yet reach the end of our computation, so we just keep any value, or we are branching, right? We are recursing down. We take some value that we have just computed, and we run a function that inspects this value and tells us what to do next. So that's the branching part. So this is how we model tree. Now, in this part, we just model what we said. We need to somehow get when we describe our computation as a tree, we need to make a way to get the value out of this tree finally. And here is our other requirement, that we need to prove that that what we're producing finally is the instance of our ADT. So we can put that validation on type level here by just demanding a proof from the compiler. So we have basic structure. Next step, implementing it. Now, implementation is very easy. You just follow the types. And that's basically it. There are some interesting things here, like how do you short circuit? How do you break from the computation when you reach the ADT? Well, you just return nothing in this case. You just return the same stuff that you have. You don't try to do anything. You don't run functions. You don't do anything. You just return yourself. That's how you implement short circuit. But in fact, there is no other way to implement this case if you follow the types. There can be no other, well, pure implementation. And here's the interesting part. Here's how we model, recursing deeper and deeper into such a tree. Just follow the types. There will be only one pure implementation that can emerge. Now, when you follow the types, you have probably seen that coming. When you just follow the types, what you get is stack overflow. So now, you follow the types up to a point, I would say. And here comes the part where there's a lot of debugging, head scratching, and so on. But, well, the problem is here, actually, right? We are recursing by nesting functions. So if we nest them long enough, we create tree that's, that has, height that's sufficiently large. Then we just nest and nest and nest and nest, and we try to compute whatever we have in this tree. We'll end up with Stack Overflow. So after some head scratching, you basically discover trampoline. Trampolines are structures that trade stack for a heap, basically, thus making you stack safe. And it turns out that such a generic structure, trampoline structure, is in Cat's library. It's called eval. So you just apply eval where possible and follow the types. It starts to work, but we just created something called Schlemmer the painter algorithm. I'm not sure if you heard the term. Did you hear the term Schlemmer the painter algorithm? So there's anecdotal description of what that is. So Schlemmer was the painter hired to paint lines on the road. So when he was hired on his first day, he did an exceptional job. His boss complimented him for drawing, line well above the average worker line. He painted such a long line on his first day that he was appointed to be an exceptionally good worker. But on subsequent days, his performance dropped and dropped and dropped, up to a point where he painted almost nothing. And his boss called him and asked, Schlemmer, why are you slacking? You were such an exceptional worker on your first day, and now you're doing nothing. What's happened? And he said, oh, sir, sorry, I can't help this, but every day I'm further and further away from the paint bucket. So Schlemmer, basically what he does, he didn't figure that he needs to carry his paint bucket with him as he paints those lines, so he just unproductively runs back and forth without doing nothing. That's what we are doing here. Basically, So the example that showed us that we are not stack safe is computing numbers bigger and bigger and bigger. Now, if we blindly just apply eval, we created an algorithm that computes the first number, which happens to be 0, and passes this 0 all along the chain of flat maps in a stack safe way to recreate the whole structure. Now it takes 1, which is the next value, and passes it all the way down on flat maps to recreate the whole structure of height 1 less, and so on, so on, so on. So it's basically a quadratic algorithm. If you run this algorithm on this example, you would wait for eternity to get an answer. Because every time we're recreating and recreating unproductively structures, 1 less, 1 less, 1 less, we're doing it n times, where n is number of nodes, and we so that's basically a quadratic algorithm. No one would use that. We have to be smarter than that, so let's just rip off whatever Free does. Free doesn't have these problems. So we go once again to Free Monad implementation to basically copy what they did. And it turns out that what they did is a very smart thing. They just divided computation into 2 parts. One is stepping through layers, where they peel off layers of your tree and return either continuation of your work without having to recreate the whole tree once and once and once again, or the value. So we do the same thing, and then we feed this function that steps through the layers of our tree to a tailRecM, a monadic recursion function. And so basically we just copy whatever Free does, and it works. Finally, well, we'll have to re-implement some parts basically, but finally it works. But creating structures like this is no easy task. It works, but you don't yet release it to your colleagues. You need to add some useful combinators. Now, with combinators, it's easy to work around them. You just create, you have created your basic map and flat map. You just create more and more high-level combinators based on those, and then you create more and more high-level combinators based on those. Basically, you just copy whatever your colleagues are familiar with. You need some useful constructors, so they don't complain that they can't create easily your instances of your structure. Just go through your code base and see whatever they're using. After that, you're not yet done. You need to add some syntax so it's easy to use, and add some laws and test them. And I need to stress that this point is really important. How do you think I knew that we are not stack safe? I didn't think of it in the first place. It didn't come across that I need to check my structure for stack safety. No. I implemented my structure as a monad. The only reason I did that is not because someone might like to abstract on my structure. No one would do that. I did it to have access to monadic laws. And monadic laws test a lot of corner cases, and that will help you. Help you discover issues like, stack overflow, or whether actually what you wrote is sane. But now, since I'm writing my own combinators, I can add laws governing their intended behavior as well in abstract terms. Now, when I run Scala check or discipline on that, I will have a lot of automated tests based on my, documentation, so to say. That's a great thing because it gives me confidence to refactor my structure again. So this point is very important. But after you did that, you can finally release it to your boss, your company, your colleagues, and they start to apply to their code base. So hopefully code gets smaller. Here is what it was. On top and on the bottom is how it's rewritten. And I actually write laws for such examples to check whether they are actually equivalent. So that's another point in favor of using laws. So hopefully code gets smaller, it gets more neat. They don't have to care about things like calling pure because you can handle it for them. They cannot escape it. They cannot write code that, for instance, does not return an instance of response or do some strange things. it's tailored to what they do, so it's smaller, more compact, more, well, usable for them. They rewrite it, and you think you're done, but you're not done, because they will very soon start complaining that it's very slow. And in fact, one-liners are like 4 times slower than EitherT equivalents. Longer programs are 30% slower. You need to absolutely use JMH, which is a Java micro benchmark harness. That's wonderful stuff. There is a build, there's SBT plugin, so you can use it in your build. You need to use async profiler to give you a beautiful flame graphs. And after you use that, you can inspect where your code is wasting all this time. Now, in my case, it looked like this. Here we have black holes, which are basically black hole in JMH terminology is a non-optimizable by JIT, work non-optimizable by JIT. It's just what I do to simulate workload. That's what I put on purpose, so I can't eliminate that. But here I see a flame leaks. What are these? Oh, well, this is our eval. Eval is very, very slow. What do I do? Well, I go back to free monad again, because free somehow doesn't use eval, so I can just copy what they do. And what they do is they don't use eval, because all the hard work is already handled by tailrec_m. Eval is artifact from times where we didn't know what we were doing, basically, and we were just experimenting. So you just write everything to use pattern match. Pattern match is much faster in this manner, but basically that's copying whatever free monad did, and now your performance is comparable to EitherT, and that's what you release to your colleagues. And they are happy ever after. That's how you will end up looking after you finish all this work. One more word, may I? Thank you for coming. I hope you learned something. I'm not sure what's to learn from this talk, but I hope you learned something. But if there is one takeaway point I would like to make is that you can think of computations and style of computations as data structures, basically. And so you can write them, you can optimize them, you can write very abstract code that probably you wouldn't write anywhere else, learn a lot in the process, and, well, help your colleagues. So if you see opportunity to do that, then just please do that. You will learn a lot. I guess that's my point. Thanks.
Thank you for your talk.
Thank you.
Among the others, you had a problem with composability. Does this approach solve this?
This approach sidesteps this. You don't have to compose anything, because at the end, you don't have any hierarchy to compose. You just have a login response, but you don't have to compose login response with, I don't know, unlogin response, right? Because they are two separate things, and you probably wouldn't have to compose them. Even if there is no, so to say, no type to compose on. You just return, at the end, you'll have something like future from login response and future from other service response, right? So there is nothing to compose it, basically, because how would you compose login response and other response? But if you need to, you can, but you don't have to pack it in some structure like either or something like that, because they are totally independent. So in this way, this issue is sidestepped, right? By not needing to compose, basically. You somehow might want to compose errors, but there are no errors here. They are just responses, separate responses. So it doesn't help it. It sidesteps it, basically. That's what I would say.
Thank you for your talk. So I want to ask, what is the amount of time you have?
I've spent, yeah. Well, if I recall correctly, it took more or less close to a month to do, from the initial design to, having tests, releasing it on Bitbucket or wherever we release that, creating a GitHub repo. So end to end, it was more or less 1 month plus some big bug fixes if one of my colleagues found something. I would say it's more or less a month.
Thank you. Was it suitable to incrementally update your code base?
Yes, because well, maybe I'll go back to an example like this one, because everything is local to method. So when in previous examples you returned, you either had some dependency on some implicit or something like that, or you needed to return either. Here it returns just a single value, which is not either. It doesn't have any implicit dependencies. So everything you do is local to the method you do it in, basically. So you can just take one method, refactor it. It won't change your signatures. You won't have to, return some higher kind of things like either. You just return a single value, which is an instance of your ADT, and you're done, and you go to the next method, and so on, so on. No implicits, no real, functional dependencies. So it's suitable for that, by the virtue of being local to whatever you do. Oh, by the way, this code is on GitHub. I'm not that proud of it, but if you want me to give you a link, that I can. I'll just write to Victor and then put it on site. Oh, sure, yeah. No, okay. I guess that's all. I think links will be on Scala website, right? As well, but yeah, I take a picture. So once again, thank you very much.